But yeah, I think that last few years I'm kind of exploring new areas. So I started working on Web3 uh, about I think 2.5 years now, right? So that's what I'll be talking about today. It's going to be a high-level talk. During our PC meeting, one thing that was discussed is that most of the students go on to pursue machine learning, right? And one of the ideas is that we want to paint a picture that there is a world out there apart from machine learning, especially for the folks that work in this program analysis and program transformation world. And there are exciting opportunities, exciting challenges. You can pursue nice career in other fields apart from machine learning, right? So in this talk, there is going to be nothing about machine learning. Okay. All right. So, most of us know Web3 as, okay, Web3, people understand that Web3 is a blockchain. Web3 in and itself is actually much more than blockchain, but blockchain is one of the centerpiece around which Web3 is built. So when I Google for blockchain, this is the definition that comes up. It says that a system in which a record of transactions, especially those made in cryptocurrency, is maintained across computers that are linked in peer-to-peer network. So I feel that let's say that somebody has just finished a BTech. Seems like there are a lot of buzzwords, but it doesn't really tell you what it is. What does it really mean? So me, being myself a computer science student, I would say that, okay, when I looked at blockchain and when you remove all of these, buzzwords, etc., this is what I feel like. What is it? It is just an execution trace of a deterministic state machine. Here, deterministic is the keyword. And we will come to that why this determinism is required. Okay. So when you say a block in a blockchain, what is it? It is exactly this, right? So it's a block. You have an input state. You execute your first transaction. It would go to another state, another transaction, another state, and so on and so forth. At the end of the block, you reach this S5. So S5, after this block is produced, the state of the blockchain is actually S5. So that's what it is. It's an execution trace. Right? You know that in a state transition system, even in a deterministic state transition system, there could be multiple output transitions. But since this is a trace, that's why you just have one transition, right? It's deterministic. So given one input state, you always produce only one output state. So once your block look like this is what a blockchain is, where essentially the output state of this block becomes the input of the next one. And the way actually the chain is maintained is you compute a hash of the previous block, put it in this block, and so on and so forth. That's what it is. Just a trace of a deterministic computer, deterministic state machine. Okay, so what has that got to do with program analysis, right? So again, people are told, okay, what is program? And they'll be, oh, it's a set of instruction, recipe, blah, blah, blah. From a computer science perspective, the way I see it, and I think that, most of our enthusiasts, especially those like me coming from formal verification background, programs are state transformers. So imagine the one-line program, x is equal to x plus 1. That's it. That's my program. What does it tell? It says that if you give me as input, I'm sorry that this color is not visible, but it says x is equal to 0. Here, the is equal to sign is mathematical equality, whereas here it is the assignment. So your input state is x is equal to 0. So if you give an input state where x is mathematically equal to 0, and if you apply this transformer, it becomes x is equal to 1. Similarly, x is equal to 1 it will transform it to x is equal to 2. If my x is an 8-bit integer, now what happens if I apply the same transformer to x255? And depends on how I want to define the semantics, right? those who have programmed in C or something like that, you know that if, let's say that, we have assigned integer, then integer overflow, the compiler is free to do anything it wants. The C standard says that implementation is free to do what it wants. But if it does what it wants, then it is non-determinism. Undefined behaviors are not allowed in blockchain, right? Why not? Because if we do not have deterministic operational semantics, what would happen is that somebody gives you this trace, and now you say that you are trying to replay that trace. You are saying that, okay, let me start with the genesis block. I'll execute all the transaction, then block 1, block 2, etc. Do I end up in the same state? Maybe not. If there is non-determinism, then you will end up in a different state. One of the properties that blockchain gives you is that you should be able to replay, and that can happen only if it is deterministic. Irrespective of the hardware you run on, irrespective of the time at which you run on, it should always produce the same state, because it's a trace, right? Deterministic of a deterministic machine. So with that in mind, now let's come back to this thing. But why? I mean, so what? If somebody executes at a different time and will produce a different state, like, big deal. So see, one of my friend, right? He runs a company. He says that I feel threatened that, like Google is owning all my information. So what he's saying that I'll store my photographs in Google, work-related stuff in Microsoft OneDrive, maybe some other things in some other private cloud. Now, why did he do that? Does he trust Google alone? No. Does he trust Microsoft alone? No. But essentially what he's trying to do is that he's saying it's a distributed trust. People abuse the word trustless in a blockchain system, but really what it is, it's a distributed trust. You say that, see, this one guy can be corrupt, 2 guy can be corrupt, 3 guy can be corrupt, but if 100 guys are doing the same computation of a deterministic machine, and you are pinning your hope that not more than certain threshold is corrupt. Depending upon the scenario, you want that threshold to be 33 or 49. It'll depend what problem you are trying to solve, but that's what it is. So it guarantees you that in that distributed trust, if the number of corrupt parties, if it is lesser than this threshold, then you can put a faith in the entire system. It's a distributed trust. You know that it is going to compute exactly the way it's supposed to. That is why determinism is important. Because if, let's say, that determinism is not there, one node computes it, another node, because it is slow, because it is a different hardware, it computes the same thing. Just 1 millisecond later, it's possible that it's going to compute a different state. So even though both the nodes are honest, they won't be able to tell you that, yes, like we agree on the final state of the blockchain, even though they are not corrupt. So that's why determinism is important. So if the determinism is so important, so now there's the new definition I would the way I see is that it's an execution trace of a deterministic state machine. But this trace, in the state that it went through, the journey it took, it is agreed upon by a network of distributed, possibly heterogeneous, and decentralized computer. When I say decentralized, they are independent of each other. If you run 100 computers like Google, but all of them are under one jurisdiction, one entity, then if the Google is corrupt, then all these hundreds are gone, right? So important property that it's a distributed trust means that there has to be decentralization at all levels, jurisdiction, geography, and a lot of other parameters. So now if I want a determinism in my programming language, then these are the things that is going to give me problem. Floating point arithmetic, right? Anybody who has worked around floating point arithmetic, you know that it's a very hard thing to tame, right? So actually there are programming languages, new programming languages like Move, they do not even have floating point arithmetic. No floating point arithmetic. If language does not have it, you cannot do floating point arithmetic. Right? Signed integer arithmetic. Now, I mean, to be honest, there is nothing wrong with signed integer arithmetic. It's just that you need to define its semantics in a deterministic fashion. So you either say that I'll accept a wrap around semantics, or I'll say that basically whenever it overflows or underflow, I will say that the transaction will abort with an error. And since the word transaction comes from essentially the database, that either whatever the program that you have run and all the state mutation that it has done, either all of them will be committed to the blockchain or none of them would be. Atomicity property. That's why it's called a transaction. So these are the things that sort of known to cause problems in a traditional computing world around undefined behavior, right? Concurrency. If you have multiple thread concurrent or parallel computation, and if they race, you might end up in a different state because of schedule non-determinism. Now you see that the fundamental part is data. So if somehow you figure out that you can do things concurrently, but still be able to define the end state in a deterministic fashion, it doesn't explicitly forbid that you can't do things concurrently. But this is the semantics. Right? And also interaction with the external environment. That means that basically you cannot have an instruction inside a blockchain which says that, connect to the network and see that what is the price of Reliance stock. Because again, if there is a difference of 1 millisecond, even the honest computers would not agree what is that price. And that is where oracles come in, where you put the information from the external environment as an input to the blockchain. Right? Now, why am I talking about determinism? I'm talking about it because if you are a programming language person, if you want to design a new programming language for smart contract, you have to take care of these things. You have to define it. And in this space, actually, people are defining new languages. People are saying that, okay, let me think about it from ground up. And if you are one of those, you like to design programming language, you keep this into mind. As long as it is deterministic, it's fine. All right. And also, yeah, it's Turing complete. Most of the programming languages that are for smart contract, they are all Turing complete. All right. So if they are Turing complete, then I have a problem. How does it terminate? If all of the machines are running the code that I'm giving it, the function may be very long running function. It may or may not terminate. So if somebody messes up their smart contract, and if there is an infinite loop, it would never terminate. So that's a problem. And the way the blockchain handles this problem is that, say, you know what? We are going to attach a counter, which I'm calling gas. Gas measures resources in terms of storage, in terms of bandwidth, in terms of computation. And it says that while your program is running, the moment you consume this much resource, the moment you consume this much gas, that's it. If the transaction has not completed successfully by then, if your program is uncompleted successfully by that time, it is out. The transaction is aborted. Right? So that is how they sort of, you take care of this. Terminate. I'll take questions later. Yeah. So that is how, it deals with the termination. So usually in any programming language or virtual machine, what they define is a gas cost table, right? So for every instruction in the virtual machine, it provides this function that basically you give this instruction, it will tell you a natural number which represents the gas. Absolute value doesn't matter. What matters is the ratio. You want to say that one operation is costlier than the other. Absolute number doesn't matter. Okay, as long as it is positive. So if I have gas, I'm fine, by the way. My digestive system is fine. But see, ultimately it translates to money. The more in the blockchain system, the more gas you consume, the more amount of real money you have to pay to the network. You are paying to the network for consumption of resources. So you say that, what? How do I arrive at the same output state, but by spending less gas? That is gas optimization for you. Okay, so this problem is for gas optimization, that I want to achieve the same output state, but I want to spend the least amount of money and therefore the least amount of gas. So it's an optimization, and typically the way we do optimization is that okay, to make my programs fast, but many times to make your programs fast, you increase the size of the program. Now, because in blockchain, the gas is measured both in terms of the storage and the computation. So if we increase the size of the program, that is also a problem. So it's a bit tricky, but it's a nice challenge for those who are into program analysis. Right? It's an optimization problem. You optimize for this function. We have gas cost table. You try to minimize the gas while preserving the output state. Right? Okay. So now you see that from the user experience point of view, a user, before the user submits a transaction, it wants to say how much gas I should pack in a transaction. Right. So you say that basically I want to, run my smart contract, but I am willing to pay only this much. That's what you are indicating to the network. But for that you require some kind of estimation from somewhere. Right. So that is also another problem. How do you estimate gas? The thing is that in general, the problem is undecidable. You can't do it. Right? And the second problem is that, so practically what people try to do is that when you try to send to the network, usually you do not directly send to the validator nodes. There are RPC nodes that sit in between. They provide the estimation service via simulation. But when they simulate in the input context which is available with them. But you know that the transaction is never going to get executed with that input state. So even if the RPC node is giving you via simulation, so it's actually running and giving you the estimate, it may not be correct. Right? So this is another nice challenge from the point of view of program analysis, that try to estimate. You know that you are going to be wrong because the problem is undecidable in general, but try to estimate as accurately as possible. And both the user as well as the network benefits. User, I mean, we know that the user knows that how much to pack, right? Now there are use cases where network want to say that, okay, I want to reserve certain amount of block space. Block space typically, you measure in terms of gas, not the number of transaction. So if you want to provide guarantee to certain parties that I want to reserve it for you, etc., you require this to be accurate, right? Because otherwise somebody is overpaying, right? Either the network or the user. Right? So those kind of problems are there. It's a very interesting problem, not a new problem. People have worked on it, but this is something that if you are interested in program analysis, something to look at, right? The beauty is that the gas cost table is known, so you know that what you are optimizing for, not some random benchmark or random hardware. You are optimizing for a specific known function. All right, so let's talk about the role of various compilers and virtual machines. So there are compilers which translate high-level programming language, like Solidity is there, Move is there, etc. And then there are corresponding virtual machines are there, and you want to translate from that high level to low level. So there the compilers are used. It's not only for translation. See, people design this compiler new program. I mean, designing a new programming language actually entails that you have a compiler for it. And languages like Move programming language, they are designed with certain smart contract security upfront in mind, and they try to achieve better safety and security for your smart contract via type system. Right? So that is very important that, okay, if you are writing a compiler, how can you design this whole thing so that I provide a better developer experience, right? Okay, so now you say that, okay, you know what? There are people who want to use Move because it offers better type checks, better memory safety and whatnot. But we already have a lot of legacy. A lot of people have written a lot of Solidity code. What do I do with it? So then people say, all right, you know what? We are going to write kind of, EVM interpreter inside Move. People have actually done that. So that's a nice space to look at that. When you already have a lot of programs available in various programming language, how do you get all of them to run on the target VM that you are supporting as a chain? So for example, Fractal, I think it's by Movement Labs, and they have done work, but that's not the single work. I mean, other people are doing it. And yeah, I mean, enabling smart contract programming language to kind of, I mean, people say that web assembly is near native. People say, okay, running on browser, but in a safe manner, how do you access the native capabilities of running codes faster? So now people say, okay, we'll translate, Rust and C and C++, etc., down to a subset of WebAssembly, not really WebAssembly. The reason why I'm saying subset is that you remember that, we have to have deterministic things, right? So a lot of people, I mean, there are projects that are doing this, that have done this, but it's a nice space to look at because if you want to build a high throughput blockchain, you want all of these smart contracts to run as fast as possible. And also remember, I'll go back to the concurrency thing that, see, blockchain does not explicitly forbid concurrency. All it demands that the output state should be deterministic. So then people have things like block STM and things like, so they speculatively run transaction parallel. And if they conflict with each other, you know that, okay, if they are conflicting, I have a block, I have the ordering between them. So now I'll follow the order between them. And that's the kind of stuff it tries to do. Yeah. And this, very close to my heart because I have worked in this space, I don't know, about 20 years now in the safety. I'm a formal verification person. Okay, so static analysis tool for vulnerability detection, and there are quite a lot of tools available in this space. Many of them, what they do is that if the vulnerability was available in the past, you build some kind of a pattern, you try to do pattern matching, or you do symbolic execution and things like that, right? So you have tools in this space, and it is not that, okay, that is sufficient. More and more tools are certainly required because more and more platforms, more and more languages continue to emerge. And it is not that all these transpilers and compilers, etc., they are verified. They haven't gone to as much scrutiny that LLVM or GCC has gone through, right? So certainly there is a lot of things that can be done over here. That is this transformation itself sound? And hopefully tomorrow, Professor Supra is going to talk about translation validation. Right? And you have model checkers, mostly academic community work in this space. But also there are smart contract auditors. So there are audit companies. The company themselves developing usually don't do it, but they give it to auditors. Maybe they use some of these tools which do a very rigorous analysis because it's a state transition system. You try to do symbolic analysis of this state transition system and try to see that whether there is any possible execution in which your execution can fail. Right? And then there are provers. One thing that I like, because I personally look at Move programming language, it comes with Move prover. It uses Z3 as a SMT solver. So you can specify your properties and it will be able to, either will give a counter example or it will say that, yes, this property holds, irrespective of what the input is. Okay. So very quickly, I mean, just to give a taste that why this is the safety and smart contract is important. You see that this is a lottery related contract. This is the last slide. I'll just finish. So essentially, let's say that somebody gives up multiple tickets. Now you are checking that you are indeed the owner of these lottery ticket, whether the lottery ticket is claimed or not. These two things you are checking. And then what you are saying that, okay, what is the corresponding reward for this ticket? The multi-claim reward part, by the way, this is a real code. Okay, in pancake swap protocol. I mean, they fixed it, but it was there. And here you are marking all the tickets as claimed. And now you give the total reward. I mean, on the face of it, everything looks fine, right? See, the problem is that there is no check that these tickets are unique. So if I have one winning ticket, I can just make copies of it and pass. Now you see that, will it pass this check? Am I the owner? Yes. Is it claimed? No, because the ticket is claimed, that is being set after the loop. So that means that if I have one winning ticket, I can make multiple copies, multiply my reward, and just be happy, right? And this is just one example. There are a lot of such subtle bugs are out there, and for which more and more investment should be made in rigorous analysis of programs. And I'll leave you with this thought. Alan Page has worked for, I think, more than 2 decades in Microsoft as test architect. So you can just read for yourself, right? That's the end of the talk. I'll welcome any questions, sir. Yeah.
I don't know if I understood it correctly. The gas, is it not conflicting with your deterministic determinism? Gas, you are saying that, okay, if I run out of resources, then I'm saying it's abort. So is it not conflicting with your deterministic requirement?
No, it's a fully deterministic semantic, right? If you run out of gas at any point in time during your execution, you abort. It's deterministic thing.
No, that's correct. But then the determinism is lost, isn't it? Like,
No.
No. Okay.
When you start in the same input state, you are guaranteed that the transaction with that input state and that much gas is either always going to fail or always going to succeed. There is no non-determinism here.
Then what about the optimization then? If you could optimize, then you can optimize in the beginning itself and then give that as your resource constraint?
So optimization has to be done actually before you sort of give it to the chain, right? So when you are writing a code, why do we do code optimization? We say that, okay, we'll do code optimization, prepare an executable so that it runs fast. The same idea over here. You do the optimization so that I know, see, all optimization, right, whether it is for speed or for gas, it is actually what you are trying to do is not make it faster. You are making it faster on expectation. On expectation being the keyword over here. Because you do not know which path is going to be taken. Imagine that somebody has given you a probability distribution across all of these various paths, right? What you want to achieve by this optimization is that on expectation, the gas consumption should be lower, or on expectation, it should run fast. Are you guaranteed? No, because it's a probabilistic space. And nobody has given you that probabilistic distribution. That's why we are doing the simulation, right? So, yeah.
So if gas estimation is an undecidable problem, how is it handled now? Are there some strategies with which it is being handled?
Yeah, very good question, right? So as I said that, like practically the way things are done is the user typically uses estimation service by RPC node. In that estimation, what is being done is that whatever is the blockchain state is available with the RPC node, it executes it and it tells that this much gas was consumed in this execution at the end of, if the execution had happened at the end of this block, right? But you know that the actual context might differ, so it's an estimation. So typically what user does is that it takes this estimation, it adds some buffer that maybe if the input context changes and maybe it might end up spending more gas, you add some buffer for practicality. So that is how it's being handled. But however, you can always try to do some static analysis, try to be as over approximate, but try to be as accurate as possible, right? So those kind of problems.
Hello. You mentioned that there were a few projects that try to emulate a virtual machine inside another one. For example, the EVM inside the move VM. What is the advantage of doing that as opposed to just running 2 VMs? Like if it's EVM code, then run it in an EVM itself. If it's move VM code, then run it in a move VM.
Excellent question. So see, typically what happens is that these EVMs, these implementation, etc. So they have their own storage layer. So once if you are running 2 different VM, you are creating a partition in your state space. Now many times, basically, if you want atomicity and various other things, it becomes not so easy problem, right? That basically now this VM has a certain way of accessing its storage layer, how do you access another storage layer which is not compatible to that, right? I'm not saying it can't be done. So maybe you can do it that way, that create a common storage layer and make both of these VM compatible with this unified storage layer that you have worked on. But if you don't want to do that, this is another way you can do it, right? So you just emulate.
Well, let's thank Saurabh once more.